Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to the class, and today we will learn about the applications of Huygens principle. We will see what are the applications of Huygens principle, how successful it was, and we will see the phenomena, how it explained the phenomena of reflection, refraction and total internal reflection. Now the first application which we will learn today of Huygens principle is in refraction. We will see using Huygens principle how to verify the law of refraction. Now we will start here with a plane wave, and the wavefront of this plane wave is represented by this AB line here. Suppose this is a cross section of a plane which is in the form of a line, and this A1 B1 wavefront falls at a angle at an interface S1 S2. S1 S2 divides the two media. Okay, above S1 S2 there is a medium of different refractive index, and below S1 S2 there is a refractive index of different refractive index. Okay, and the light or the wavefront falls from the top medium at this interface, and then it get refracted into the second medium. Okay, the second medium is drawn here with a shaded color, the brownish color. Okay, now let tau be the time taken for the wavefront to travel the distance B1 B3. Yeah, sorry, it is not disturbance, it is distance. Okay. Now this is the A1 C1 B1 is the wavefront which is falling at the interface, and since it is this wavefront is falling at some angle, the part A1 of the wavefront will fall earlier as compared to the point B1. I repeat, the point A1 of the wavefront will fall at the interface earlier as compared to point B1. Yeah. Now the point B1 will take some time to reach at the interface, and this point B1 will fall at point B3 at the interface. Yeah. Now suppose point B1 takes time tau to reach at B3. Okay, and suppose the speed of the wave in first medium is V1, while that in second medium is V2. Okay. Since point B1 is taking tau time in reaching to point B3, the total distance travelled by point B1 will be equal to V1 into tau. Tau is the time and V1 is the speed in the upper medium. Therefore, the total distance would be V1 into tau. During the time period tau, the A1 would have gone deeper into the second medium. Okay, the A1 will reach to point A3 within the medium, and this much distance would be travelled by point A1 in medium 2, in the second medium, and since medium 2 is of different refractive index, the wave will propagate with different speed in this medium. Suppose the wave speed is V2 here, therefore in time tau, it will travel a distance v2 tau, okay, and therefore a1 a3 would be equal to v2 into tau, and this is what is written here. Yeah, b1 b3 is equal to v1 tau, while a1 a3 is equal to v2 tau, and a1 a3 would be different from b1 b3 because of different velocities. Yeah. Now let us consider two triangles. The first one is b2 c2 b3. Yeah, this is the first triangle and this is our second triangle. Yeah, c2 c3 c2 b3 is the second triangle. Okay, but before moving ahead, let me point out a few things. Now this is the wave front which is moving in this direction, and then after refraction it got a bit tilted and then it is traveling in this particular direction. We picked some random point C1 on the incoming wave front, and we assume that it took tau 1 time to reach at point C2. Yeah, and therefore C1 C2 would be equal to V1 into tau 1. Yeah. We also assume that angle of incidence of this wave front at S1 S2 interface is I. Therefore, this angle would be I, which is our angle of incidence, and suppose the angle of refraction is R, therefore this angle would be R, or this angle would be R. Okay, having known this, let us write the expression for sin I by sin R using these two triangles. Okay, what would be sin I in this upper triangle? This is our upper triangle, this is the 90-degree angle, and how did we form this triangle? We just drew a perpendicular from here to here. Yeah. Now what we know is that sin I would be equal to b2 b3 by the hypotenuse, which is c2 b3. Similarly, sin R would be c2 c3 by c2 b3. Okay, and since this is common, c2 b3 is common in both the denominators, it will go away and we would be left with b2 b3 by c2 c3. Now as we know, c2 c3 is v1 into tau, and this is equal to c2 c3, therefore b1 b2 would also be equal to v1 into tau, and therefore b2 b3 distance would be equal to b2 b3 would be equal to the total distance v1 tau minus v1 tau 1, and we can take v1 out, then we will get v1 into tau 1 minus tau 2. Okay. Now similarly for c2 c3, c2 c3 would be equal to a2 a3. Yeah, c2 c3 would be equal to a2 a3, and from here we can get that c2 c3 is equal to v2 tau minus v2 tau 1. Okay, this is what is written here. Now from here the tau minus tau 1 will go away and we will have v1 by v2. Okay, and which is our Snell's law. Okay, now you may see that in the figure we have this type of structures, and which shows that which shows the wavefront. Yeah, the secondary wavelets emits from the wavefront. This is the primary wavefront, A1 B1 is the primary wavefront, and from each point secondary wavefront emits, and these are the traces of the secondary wavefront. Yeah, and then we draw an envelope on this secondary wavefront, and this envelope is A2 C2 B2. From A2 C2 B2 again new wavefronts, new secondary wavefronts emanates, and these are the part of the new secondary wavefront, and then we draw this envelope on top of it. Similarly, this dash line also A4 C4 B4 again represents the newer position of the wavefront, and this is how the wavefront propagates, and this is following from the principle, Huygens principle. This is how the wavefront propagates. Yeah, the wavefront is started from A1 C1 B1, then it reached to A2 C2 B3 B2, then A3 C3 B3, and then A4 C4 B4, and so on. Yeah. Now, having known the expression of sin I by sin r, which is equal to V1 by V2, we know that it verifies the Snell's law. Yeah, and now it is observed. Now, in the figure itself, you can see that here, since this is a denser medium, we assume that it is denser. Yeah, and this is a rarer medium. Then what will happen? This distance V1 V2 tau, this distance would be smaller than this distance V1 tau, and therefore r would be smaller than I. Yeah, angle of incidence would be larger than angle of refraction. Okay, this we can just from the geometry we can get this information. Okay, and this is true for a case when light is traveling from rarer medium to the denser medium. Opposite would be true for the case when light travels from denser to rarer medium, and therefore the angle of incidence would be larger than the angle of refraction, and consequently sin I would be larger than sin r, which implies that V1 is larger than V2. Okay, which says that if angle of incidence is larger than angle of refraction, then V1 is larger than V2. It means the light will travel faster in the rarer medium as compared to the denser medium, and therefore Huygens principle predicts that speed of light in a rarer medium is greater than the speed of light in the denser medium, and this prediction is contradictory to that made by corpuscular theory, and the prediction made by Huygens theory is correct. Yeah, and it turned down the Newton's corpuscular theory. Yeah, Newton's corpuscular theory failed here. Okay, and Huygens principle correctly predicted the relative speed of the light or the relative speed of the wave in different kind of medium. Yeah, if a medium is denser, the light will propagate slower there. Now, if c represents the speed of light in free space, then the ratio c by v, we know it is called a refractive index of the medium, n is equal to c by v, we have already discussed it. Yeah. Now, since in the phenomena of refraction they are involved two media, therefore we will have to define two index of refraction. Yeah, the n1 and n2 are the refractive indices of the two media. Yeah, the n1 is for the first medium, n2 is for the second medium, and v1 and v2 are the corresponding velocities. Then we know that Snell's law is sin I by sin r is equal to n2 by n1, which is written here, but same thing can be written in terms of v1 v2 as we derived earlier, and we can also involve wavelength here too. How to involve wavelength? Now, suppose in this figure, now you see that in this figure 4 plane waves are drawn, and suppose all these waves wavefronts are separated by some distance, and suppose this r lambda 2, this is again lambda 2, this is again lambda 2, and here it is lambda 1. Yeah, this will also be equal to lambda 1 because this is in the first medium, lambda 1. Okay, what we can say is that C1 C2 is equal to B1 B2, which would be equal to lambda 1. Okay, and A2 A3, which is again equal to C2 C3, is equal to lambda 2. Lambda 1 is the wavelength of the wave in upper medium, and lambda 2 is the wavelength of the wave in the lower medium, and so on. If this is the case, then what we can do is that we can write this, yeah, from the geometry in these triangle. Yeah, in these two triangle, using the geometry, if this distance is lambda 2 and this distance is lambda 1, okay, and with the assumption that all these wavefronts are separated by the respective wavelength. Yeah, with these assumptions, or we can say that all these wavefronts represent the consecutive crest. Yeah, with this assumption, C2 C3 would be equal to lambda 2, while B2 V3 would be equal to lambda 1. And using these two triangles, we can say that sin I upon sin r is equal to lambda 1 by lambda 2, and which is again equal to V1 by V2. And from here we get V1 by lambda 1 is equal to V2 by lambda 2. Yeah, and if they are several layered medium, then we can equivalently write that V1 by lambda 1 is equal to V2 by lambda 2, which is again equal to V3 by lambda 3, and so on and so forth. And we can write Vi by lambda I for any medium. Okay. It means that the ratio V by lambda is constant in this particular case. Okay. But lambda changes when you go from one medium to the another medium, lambda changes as well as V also changes. Yeah, when we go from one medium to another medium, lambda changes and the velocity also changes, but the ratio of the two does not change. Okay. Therefore, this ratio must be representing some important parameter. What is that parameter? Let us see. Yeah, when a wave gets refracted into a denser medium, the wavelength and the speed of propagation decreases. Yeah, but this ratio V by lambda, it remains the same, and we call this frequency of the source. It is a property of the source. V by lambda represents a quantity which we name as frequency, and this is the property of the source. It does not have to do anything with the medium. Yeah, it is not the property of the medium. Okay. This is all about refraction, and we fully explained the phenomena of refraction using Huygens principle. Okay. Now, we will try to understand reflection using Huygens principle. Yeah. We will start with the same concept. Suppose this APB represents a plane wave, okay, which is falling obliquely, which is falling at an angle I. Yeah, I is the angle of incidence on a mirror AB prime. Yeah, this dark horizontal line is a mirror. Yeah, had there been no mirror, this wavefront AB would have propagated further and would have reached to position CB prime. Yeah, CB prime would have been the new position of the wavefront after certain interval, but due to the presence of this mirror, this incident wavefront could not reach to CB prime. Now, in this figure, let us again do what we did in refraction. Let us assume a random point P on the wavefront, and then this point P propagate to point P1 here on the mirror, and this angle I would be the angle of incidence, and suppose the time the point B takes to reach B prime is tau. Therefore, this distance we call it as V1 tau, and suppose here the time is tau 1, therefore, this distance would be V1 into tau 1. Okay. Now, there is a one correction. Instead of writing V here, let us write instead of writing V1 here, let us write V only. Yeah, or let us repeat it here. Yeah. Similar to the previous discussion, we assume that the point B takes tau time to reach at point B prime, and the velocity in this medium of the wave is V. Therefore, this distance would be V into tau. And if we pick a random point P on the wavefront AB, then point P will reach to point P1 in time V into tau 1. Okay, tau 1 is another time. The tau 1 would be shorter than tau. Okay, and Then we draw a perpendicular from P1 to BB prime line, and this will meet here, and this distance BB1 would be equal to PP1, and which is equal to V into tau 1. Yeah. Now we will see this is what is exactly written here. BB now BB prime, which is BB prime is this distance. Yeah, BB prime distance is equal to PP prime distance, and PP prime is shown here. Yeah, this is PP prime and this is your BB prime. Okay, had there been no mirror, BB prime would have been equal to PP prime, and which is equal to AC, which is V into tau. V is the velocity of the light in that medium and tau is the time it takes. Therefore, V into tau represents the distance. Now, in order to determine the shape of the reflected wave at some time t is equal to tau, we consider this arbitrary point as stated before, and we assume that this distance is V1 tau. Tau 1 is the time which P takes to reach to P1. Okay. Now, from point P1 we draw a sphere of radius V tau minus tau 1. Okay. This whole distance BB prime is V into tau, and this shorter distance is V into tau 1. Now, we just take the difference between these two distances, which is nothing but B1 B prime. Yeah, B1 B prime is equal to V tau minus tau 1, and we will draw a sphere of radius V tau minus tau 1, considering P1 as the center of the sphere. Okay. And once the sphere is drawn, we will draw a tangent plane on this sphere from point B prime. Okay. Now, from P1 we drew a sphere, okay, and with this sphere we drew a tangent, and this tangent is passing or touching this sphere at point P2. Okay. We know that BB1, which is this distance, this is equal to PP1 is equal to V tau 1, and the distance B1 B prime is equal to P1 P2, which would be equal to V tau minus tau 1. Okay, P2 is this distance. This is P1 P2 distance. This distance would be equal to B1 B prime. Now, let us consider two triangles here too. Yeah, what would be those triangles? This is the first triangle, and this is our second triangle. We will consider these two triangles. In these two triangles, this is a 90-degree angle. These are right angle triangle. These are the 90-degree angles. P1 B prime. This line, the base. P1 B prime line is common to both of these triangles. Okay. P1 B prime is common, and this side is equal to this side. P1 P2 is equal to B1 B prime. The base is common. One side is equal to one side of these two angles is again equal. Therefore, two sides are equal, and since they both are right angle triangle, one angle is also equal, and therefore, the angle of incidence would be equal to the angle of refraction. I would be equal to R, therefore, and which is nothing but the law of reflection. Okay. Therefore, using Huygens principle, we again proved that the angle of incidence is equal to angle of reflection, and which is the law of reflection. Okay. And what did we use? We used only the concept of wavefront. We used only the principle, Huygens principle. Yeah, we started with a wavefront AB, and then we assumed that the one point at wavefront is taking certain time in reaching to the mirror, and a random point again taking certain time in reaching certain other time in reaching to another some other point at the mirror, and then we drew some geometry and we found that angle of incidence is equal to angle of refraction, and this is how Huygens principle explained the reflection. What is else which is left? Total internal reflection. Now, let us try to understand total internal reflection using Huygens principle, using Huygens theory. Okay, in this case we know that total internal reflection happens when light travels from a denser medium to a rarer medium. Therefore, this shaded region we call it as a denser medium, and this we call a rarer medium. Okay, and within the denser medium, wavefront A1 B1 is travelling, and it is made to incident on the interface between the two media at an angle I, which is our angle of incidence. Okay. Had there been no TIR, had there been usual refraction, this wavefront A1 B1 would have travelled to the rarer medium, and in the second medium it would have been at position A2 B2. The new wavefront position in the rarer medium would have been A2 B2. Yeah, and following from our previous discussion, we here again assume that point B1 sitting at the input wavefront takes tau amount of time in reaching to point B2 at the interface, and we also assume that V1 is the velocity or speed of the wave in the first medium, in the denser medium. Then B1 B2 would be equal to V1 tau, and similarly in the second medium A1 A2 would be equal to V2 tau. And we also know that velocity in the rarer medium would be larger than that into the denser medium. Why? Because Huygens proved it in our first example where we were studying refraction. We saw that the velocity of light in denser medium is smaller, therefore V1 would be smaller than V2, or V2 would be larger than V1. Okay. Now, in time tau B1 reaches to B2, and during this time only A1 will reach to A2. The new position of A1 would be A2, and what would be the distance A1 A2? This distance would be equal to V2 into tau, and since V2 is larger than V1, therefore V2 into tau would be larger than V1 into tau, or A1 A2 would be larger than B1 B2. Okay. Now, angle of incidence is given here, and this would be the angle of refraction, assuming that it is refraction is happening here. Okay. Now, let us go to the text. If the angle of incidence is such that V2 tau is larger than A1 B2, A1 B2 is this distance, okay, then the refracted wave front will be absent and total internal reflection will occur. Okay, let us repeat. If we want TIR to happen here, then this A1 B2, this must be smaller than V2 tau. Let us take sine of R. R is the angle of refraction. Then sine of R would be equal to A1 A2 by A1 B2. This is from the figure. Okay. Now, if we want V2 tau or A1 A2 to be larger than A1 B2, then what will happen? Now, if A1 A2 is larger than A1 B2, then what will happen is that the refraction will never happen. Okay. The refraction will not happen if A1 A2 is larger than A1 B2. Why? because the maximum value of sin r is equal to 1, and if a1 a2 is larger than a1 b2, then the value of sin r would be larger than 1, which is not allowed. Therefore, refraction will not happen and the wave will go into the first medium itself, which is TIR, total internal reflection. Okay. Now, the critical angle will occur when a1 a2 is equal to a1 b2. Okay, that is the maximum allowed value of a1 a2. Okay, the maximum allowed value of a1 a2 would be that it become equal to a1 b2. Okay, and in this case a1 b2 is equal to v2 tau. Okay, in this particular case we can define the critical angle, and which is given by sin which is represented by sin IC. Now, let us calculate sin IC. Sin IC would be equal to b1 b2 by a1 b2. What is b1 b2? It is v1 into tau, and what is a1 b2? It is equal to v2 into tau, and therefore, sin IC would be v1 by v2, which is nothing but n2 by n1, which is the n12, yeah, the refractive index. Now, refraction of a plane wavefront incident on a rarer medium is being considered here. Therefore, v2 is larger than v1. The angle of refraction r is greater than the angle of incidence. Now, in this case you can see here, yeah, because this is a rarer medium, and in rarer medium this v2 is larger, therefore, r would be larger than I. Yeah, the value of I when r is equal to pi by 2, we get critical angle. Okay, and this is all for total internal reflection, and we saw now here that we cannot get refraction if I is larger than a certain value, and that value is IC. Yeah, we keep increasing I. Okay, let me reframe this. Wavefront is made to incident on some non-zero angle, and it falls from a denser medium to the interface, to an interface phase, and this interface separates a denser medium from the rarer medium. Now, this wavefront falls an incident angle I. As long as this I is small, then angle of refraction is such that a1 a2 is smaller than a1 b2, and we have refraction. Okay. Now, a situation comes when a1 a2 is equal to a1 b2, and this is called critical angle, and in this case we get the TIR, yeah, and if we increase I such that a1 a2 becomes larger than a1 b2, then refraction is not allowed, because the angle of refraction is such that sin of r is now larger than 1. If a1 a2 is larger than a1 b2, then sin r would be larger than 1, which is not allowed. Therefore, refraction will not happen, and the wave will go into the first medium itself, which is your TIR, which is defined as total internal reflection. This is all for today. I end my lecture here, and see you in the next class. Thank you for being with me.